A spacecraft is in its final descent to the Martian surface when its sensors suddenly detect a lethal cluster of boulders in the landing zone. To avoid disaster, the onboard computer must beam a distress signal back to Earth, but radio waves only travel at light speed. It takes 14 minutes for data to reach mission control and another 14 for an abort command to return. By the time an engineer in California even registers the anomaly, the lander has already crashed. The sheer physical distance of millions of miles between planets makes this delay unavoidable. You cannot steer a vehicle from that far away in real time. Adding to the problem, the deep space network, the radio antennas we use to talk to our fleet, has highly constrained bandwidth. Moving massive amounts of sensor data back and forth is often physically impossible. The barrier to deep space exploration is not rocket engineering.
It is the fact that light speed delays render ground loop control obsolete during time-sensitive events. To ensure survival, NASA currently relies on the Rad 750, a legendary processor designed for extreme reliability. But the Rad 750 has severe computational limits. Its 200 MHz clock speed is roughly equivalent to a consumer desktop computer from 2001. Engineers use older technology because commercial chips cannot survive the high-energy radiation found in deep space. Outside Earth's magnetic field, subatomic particles strike commercial silicon and literally flip bits, turning a 0 into a 1. This corrupts memory and triggers system-wide crashes. While these legacy chips are stable, they are completely overwhelmed by the high-resolution data generated by modern sensors and cameras. We are trapped between advanced instruments demanding massive compute power and a radioactive environment that destroys modern silicon, crippling our ability to build autonomous spacecraft. NASA's High Performance Spaceflight Computing, or HPSC, is the specific engineering response to this deep space bottleneck. Developed with microchip technology, this architecture delivers 100 times improvement in performance per watt over the Rad 750 standard. At its core is a 64-bit RISC-V multi-core architecture, giving spacecraft raw power for complex analysis. An integrated high-speed networking switch moves massive sensor data without slowing down main processors. Specialized vector processing units allow the chip to run artificial intelligence models locally. This combination allows a probe to process environmental data internally rather than sending raw files back to a server on Earth. The HPSC acts as a localized data center designed to function without constant input from mission control. To survive radiation, the chip is manufactured on a 12-nanometer process, with logic gates specifically hardened to resist subatomic strikes. Its primary active defense against bit flips is a configuration called dual-core lockstep. In this mode, two separate processor cores execute the exact same mathematical operation at the same time. The system compares the results cycle by cycle. If radiation strikes one core and causes a mismatch, the system stops the operation instantly before corrupted data reaches the memory. The chip also manages its limited battery life through software-controlled power islands, allowing it to shut down unused sections during long cruise phases. This architecture changes the survival calculus, allowing high-performance edge AI to operate safely in the solar system's most hostile computing environments. On the surface, local AI allows a rover to autonomously classify terrain and steer around a hazard in real time without stopping to wait for instructions. In orbit, deep space probes can use local compute to rank science targets, transmitting only the most valuable findings back through limited downlink windows. For human missions, the processor acts as a reliable digital co-pilot, managing complex fault recovery systems that are instantly isolated and resolved. It is important to note that the HPSC does not create a fully self-aware or generalized artificial intelligence. True autonomy still requires rigorous software validation to prove AI models behave predictably under mission-critical stress. However, this technology ends the era of spaceflight, where machines were essentially remote-controlled drones tethered to massive teams on Earth. We are moving toward deploying intelligent edge nodes capable of genuine observation and adaptation. By shifting critical logic to the point of observation, the HPSC provides the core infrastructure for humanity's robotic emissaries to operate independently of Earth-based command cycles.